to present excellent professor. We waited Professor Kamal actually 1 month. I told my students about your expertise, about your beautiful and wonderful laboratory, which are one of the biggest in MITI. Yeah, MITI department is the Department of Mechanical Engineering. It's the biggest department, actually, it's more influential department in MIT. And Professor Kamal has a group of more than 15, almost 20 people, wonderful postdoc engineers and so on. When I visited his lab, it was so excellent environment to make a research, to do technology, to publish a paper. That for us, it's a great honor to have him here in Skoltech. Thank you for coming, thank you for your time, and please, we are waiting to excellent. Thank you.
Thank you. Yeah, thank you everyone. Yeah. And thanks, Professor Dmitry. It's actually an honor for me to be with you and for this opportunity to be here. I'm here for 2 days this time, but we have several meetings and also some lectures, and I hope we will all learn together. Anyway, in this presentation, I wanted to share with you some of the developments in robotics and automation. Of course, not everything that is happening, but maybe some selected themes. But before I start, I wanted to emphasize the importance of robotics and automation around the world. So as Professor Dmitry mentioned, we are in the Mechatronics Research Laboratory at MIT. So this research laboratory is within the Mechanical Engineering Department. And the MIT department at MIT is the second largest department at MIT. So we have about maybe close to 75 and 80 professors. And the undergraduate students, about maybe 600. The master's and PhD students, also about 600. So it's a pretty big department. Anyway, in the lab, we focus more on system dynamics, modeling, simulation, and design. We do a lot of instrumentation and control systems. And of course, most of the applications are in robotics and automation. So these are some of the companies and organizations that we have been collaborating with over the years. I want to mention maybe like 4 important trends that have been happening in the world. And one of them is that the societies around the world are changing. One is from the populations. Every country, the populations are growing. As you know, today we are maybe around 7 billion or so, and just within another 30 years, we will be beyond 9 billion. A lot of these societies are aging, and also a lot of people moving into the cities, the urbanization, and also the places, you know, in many of these countries, the young people are becoming more and more well-educated. In terms of the aging populations, you can see here that for both the developed countries and the developing countries, you can see the green and the red lines, that the people above the age of 60 is increasing. Okay, so for the developed country, and then, excuse me, for the black and the blue lines, so those are the number of people between the ages of 12 and 24, right? And so you can see that this line here for the developed countries is already leveled off, right, over here. meaning, and this happened already maybe around 2005 or so. So which means that in the developed countries already you have more, aged populations, more people above 60 than the younger people, right? And for the developing countries, the blue and the green and the red lines, so this would happen somewhere here, maybe around 2040, between 2040 and 2050, okay? So after that time, it looks like both from these predictions, both the developed and developing countries will have more aged populations. So this is important because it affects what I'm going to emphasize in a minute. The other thing is the number of companies has been increasing in many of the countries because of needs, opportunities, and also a lot of governments in some countries have been investing a lot in innovation, entrepreneurship, and of course that has made the number of companies even more. The requirements from the product's point of view have been increasing in terms of the quality, for example, the efficiency in making things. There are many restrictions that are happening today and more in the future in terms of the energy utilization and resource utilization in manufacturing, for example, and all of that would make the systems to be more and more efficient and productive. And finally, the labor cost, right? So, some of the countries like China, for example, that had benefited from their labor in the last maybe 25, 30 years. But all of that, is not the same now. It has to change. So because of this, if someone tells you that China needs people, do you believe that? Yes. They have now maybe 1.4 billion people, but because of these reasons that I mentioned, I visit China at least 2 or 3 times a year. Many companies there in all different sectors, in the food industry, the energy, automotive, different sectors. But all of them have basically the same situation when I ask about the skilled labor, the people that need to work, that are available and able to work in the factories. So that pool of people, because of the aging, because of the highly educated people, because of the number of companies, all these things that I mentioned, the pool of the available people to work in the factories is becoming smaller and smaller. Okay? So that means China has to change its model, right? And the model of the business that before some of it or quite a bit of it was based on the labor. Now it has to change to something else because that labor is not there. And by the way, this is not only in China. You start from South Korea, China, Japan, and then all the way down to Thailand. It's the same story. Okay. So what this means is that the factories and the working places have to have more and more of automated systems, whether they are from in the work environment, in the factories, in many other situations that you need to have systems that are automated and also systems that are more robust and able to work in these environments. So this is a slide that shows factories at the Boeing company. So one on the left, maybe an older one. This is showing a 747 that has been retired. Okay, and then on the one on the right, this is a plant in Everett where Boeing makes the 777 and makes also the Dreamliner, right? But when you look at this factory, it's actually very, very sophisticated factory. There is another one all in the area of Seattle that makes the 737s, right? That's in Renton. So the 737 is not a small plane. It's not a big plane as maybe the 777, but a medium-sized plane. So that one, can you guess how many planes they make, either a month or a year? Anyone?
One a month?
One plane per month. Good. Anybody else?
100.
100.
One plane per day, one plane per day maybe.
One plane per day. Yeah, I think that's pretty close. So this year they will be making about almost 2 per day. Okay? So when you go home today and try to, cook an omelet, okay, see how long it takes you to prepare an omelet. So they're making almost 2 planes a day, right? Of course, a lot of the parts, the sections, from the fuselage, the wings and so on are made, in some other factories and then they brought, to be assembled, but still assembling and testing, a very complicated machine like this one, and then you roll them out of the factory at a rate of almost 2 per day. That's very, very impressive. Yeah. So in fact, just last week I was in China, and one of the plants that I visited was also a new plant, almost maybe 7 or 8 years ago, and they make diesel engines. And these are not the small diesel engines, like a huge, okay, up to maybe 15, 16 liters, per engine. So these are big, big engines. So those ones they make about, okay, can you guess how many they make? Per day or per month or? So they make about 1 engine every 100 seconds. Okay, so you can start 1, 2, 3, 4, up to 100. You come up with an engine, but all fully assembled and all that. So they make about 400 engines a day, right? So so this is very, very important because if someone is going to compete in any industry, you have to have the people, you have to have the systems in place so that you become more competitive in that way. Of course, there have been significant advances in robotic applications, in the software and algorithms, in cars, robots, in different applications. And I'm sure that you've seen, maybe this is the Baxter robot, was designed, supposed to be for collaborative applications where you have a robot and other robots, or robots with other people in the same environment. And it was a smart robot. However, the company went out of business, last October, right? And I believe, one of the reasons because it was slow, right? To make a robot safe, at least in this design, it was a little bit slow. And of course, if the machine or a robot is slow, then it may not fit, in many of the environment, manufacturing and production environments. And then you've seen maybe the Da Vinci robot. This is from Intuitive Surgical Company in California. This is an awesome robot. I had a chance to use it, in fact, twice. Once in Boston, one of the hospitals, but playing around just with plastic components. And then another time in Chicago, where there was, a real pig, right? And then you could use this machine, to do suturing, maybe cutting, moving things. I learned how to use it in less than maybe 5 minutes. Not because I am smart, it's because the machine is smart. I did not have to learn much, right? So a few minutes, and then I learned how to use it. So there was a pig on the table, a real one, and then you can see with the vision system, it's very, very clear and very precise. The only thing is that it did not have any feedback, right? So that you cannot feel, how much force you are pushing or pulling when you are doing this operation, right? I'm sure that the surgeons who have experience, perhaps by just looking at the tissue, how it is expanding and so on, that they can tell perhaps how much force. At least when I used it maybe 6 years ago or so, 7 years ago, at that time there was no feedback embedded in this. But it makes, it extends the capability, of the surgeon, or maybe just somebody like me who is not even a surgeon. Of course, all about, the Google and the self-driving cars. But the point that I wanted to emphasize here is not the Google and the self-driving car, but that the competitors in these industries now can come from different sectors. Before, if, let's say, one wanted to look at the automotive industry, right, and you can see, for example, what kind of technologies they are developing, and to see the future in the automotive industry, then you could look, at, BMW, Mercedes, Toyota, GM, look at these, manufacturers, and then you can see in their products and so on. But today, many times you can see that the competition is coming from places, different industries. Like in this case, Google was not in the automotive industry. Started with the search engines and the maps, and then the operating systems for phones, right? And then all of a sudden, and also in a very short time, came up, with the cars. Cars that are more advanced, than the conventional cars. And Amazon, Amazon, as you know, was more into starting by selling books, and now they can sell and bring even to your home, things, maybe within 1 hour, if you can order like a TV, and you want it within 1 hour, yeah, they can bring it to you, to your home. But they are also in robotics, because they found out that using robotics in their fulfillment centers shorten the time of response. When you make an order, so that for them to fulfill your order, they can do that. And so this is, I think, very, very important for someone, that is, a lot of you, will graduate, and then to have maybe your own companies, or you go work in some other companies. So the world is changing fast, and also changing in things perhaps that we haven't planned or maybe envisioned before. Of course, the artificial intelligence, and we'll talk a little bit about it in the other slides, has been happening. AI, of course, has been around for a long time. Just recently, it has been, highlighted, because of the, computing capabilities, and also because of the algorithms that have been maybe introduced recently, right? And so now, all of a sudden, it is, high, on these topics. I have on the slide the IBM picture of the IBM Watson, or something representing or referring to the IBM Watson system, and that one, as you know, was a system that has been developed. Won the, the famous Jeopardy game in the US, about maybe 7 or 8 years ago. And since then, IBM has been developing this system to be, used in other areas, not just in the games, but also in maybe medical diagnostics, in finance, in call centers, and other areas. So, so all of this, I believe, that has advances came about because of technologies, advancements in technologies and innovation. At least two main things. Maybe one is in the instrumentation area, and then the other one is in the control. So instrumentation in the sensory systems, actuation, manipulation devices, and also more importantly in the high-performance interfaces, ways of connecting machines, to computers. And then on this side you have the computing, different kinds of control algorithms, and also planning and scheduling, different types of optimization systems, a lot of cognitive technologies in reasoning, and understanding, and of course, different types of learning and machine learning algorithms. So what we will do for the rest, this one doesn't have a clock. I was trying to look for a clock so that I can gauge my time. But anyway, yes. So I wanted to maybe discuss some things about maybe challenges and also opportunities in the instrumentation, things that are built into the materials, into the bio-inspired robots. Maybe not in details, but a few important things in terms of the communication, intelligence, collaborative robots, maybe the high-speed applications, and then maybe the monitoring and prognostics. Okay, so these are a few areas that I picked, and we can look through these ones. So the first one into an important area, you know, of taking materials and then embedding into them, like electronics, actuation, computing, communication, in all of these kind of things, so that you can have materials that are more functional, more able in that way. So this is a picture from NASA showing space, what they call the space fabric. Of course, when you hear about the different kinds of material and devices that are put in the same context, in the same environment, particularly maybe smaller spaces, one of the things that come to mind is maybe additive manufacturing, and people call it 3D printing, or maybe similar technologies of that type. Excuse me. And so I'm sure you are aware of this, so you know, additive manufacturing in general, you know, allows you to deposit, you know, there are different methods of doing it, but in the end that you can make like maybe complex parts. It allows you to maybe have the direct manufacturing of the parts, complicated parts, even maybe some parts that are maybe impossible or very difficult to make using conventional methods. Something like this, maybe some part like this one. This is from one of the sites on the internet. But perhaps allows, you know, not only the efficiency in using materials, but also maybe combining materials in many different ways. So here's a situation maybe similar to what you have in a TV screen. You have like many lines, and then on every line you have different pixels, and every pixel, if it's a color TV, you would have like 3 numbers, okay, like the associated with the red, the green, and blue colors. But imagine you do the same thing for material, that maybe at the pixel level, or maybe slightly bigger at the maybe the millimeter square area, or slightly bigger, and then you can customize, let's say maybe the material properties, electrical properties, chemical properties, magnetic properties, right? And then you can have a material that is maybe very functional and perhaps suited and accustomed to some specific application. This is an example of the additive manufacturing, and perhaps even adding all of these technologies, you know, for Amanda, who is paralyzed, you know, from the waist down. But instead of having, let's say, prostheses that are designed like for everybody, right? Imagine that you can take her unique measurements, right? Maybe by capturing them in some way, and then from those measurements, you know, custom design, you know, her specific, you know, prostheses that are fit, you know, exactly to her, right? So the other thing that I found interesting is that 3D printing, you know, of pills. There are some researchers who made some pills for diabetic people. And imagine in that same pill, you have all the different kinds of medication, right? Not only the different kinds of medication all in one pill, but each one of them with its different release time, right? So you take just one pill, and then each one of them will release, you know, at the time that is prescribed. Anyway, one of these applications was what we have done some time ago. This is a project that we had with Singapore in looking at devices or robotic systems that you see on this slide, fish and stingrays that you could use in the water. Singapore was interested in technologies to use for their water so that you can monitor and predict the status of the water of the living things in the water, such as fish and also plants, right? And one important thing is to look at them in their natural state, right? Natural state meaning not the state that is disturbed. For example, if you use a robot that is like a submarine, having a propeller, and then it drives or swims in the water, then it disturbs that environment. I can say more about this application, but one of the important things is that we believe that the creatures and the plants have maybe more advanced sensing than what we can do today, and so by observing them, you know, you can learn, you know, the behavior, of course, in their natural state, not when they are like perturbed and scared. And then perhaps you can learn from that one and then predict what might happen in the future. So these are all systems that are made out of, you can say maybe some kind of polymer, and then embedded in them, you know, the sensing, actuation, communication, computing. You can see that some of them are tethered with a wire. Okay, those are, we use them for testing so that we don't keep recharging the batteries. And then you can see things like this that are untethered, that they can go and swim in that way. So this fish, for example, the yellow fish, the top screen, so that's a yellow bass. That has only one actuator, right? Okay, because you do the model, model based on physics, how this fish, you know, would swim, and how you can, if you made it out of polymer, for example, how you can make the whole body with different material properties at different stages, where you can locate, you know, this one actuator so that when you excite it, the rest of the body, you know, just moves just in the right way. Okay, so if you used, or many people have used several actuators, okay, and then in that case there is the issue of synchronization. And what happens is that you end up having difficulty in synchronizing, and then you have a fish, you know, doing like the robotic dance. I'm a good dancer, but it's not like smooth, but it's, you know, very awkward, perhaps motions. But anyway, the Stingray was another robot, but this one gives you, you know, in the front or in the middle, I would say, a big section where you can put maybe larger batteries, you can put more electronics, and so on, than perhaps in fish. So this is how we make them. A lot of them are, you know, we use a casting fabrication, right? And then you can put, you know, the different instruments in there. Let me see. Maybe you can see on the top, maybe this one here. Okay, so you can see the head, and then this part here, different color. This is different color. From here to here, different color. The tail is different color. So these are all because each one of these materials has different properties, right? So you can imagine this one may be made where these slices are even thinner and smaller, right? And then you can get like even better performance from this. Okay, so there are many prototypes that were made and tested, and so all of this you test like in terms of efficiency, and then the thrust, you know, that is developed, and so because in the end you want to see, you know, how long of a mission, you know, this robots like this, you know, can do. Excuse me. Another one is in the communication, particularly when you have more machines and robots that are behaving at the same or cooperating at the same time. And this is a videotape. This is a clip from the internet about having a school of fish that is attacked by some predators. And this is like very amazing to me because you can see a lot of these fish, and I'm sure you've seen, you know, similar videos where a lot of fish moving and they change direction very quickly and they change speed, you know, very quickly. But then you never see like one of the fishes, you know, falling down or, you know, like bumping into each other. So it seems that they have a way of communicating and ability for feedback and perception, or perhaps they feel the water around them, and because of that, when they adjust, maybe automatically. But the importance is that they do it very, very fast, and that is, I think, amazing. And so for doing robotic applications where you have multiple systems, at least for me, the speed, it becomes like an important issue. Because when something is slow, then, it's not exciting to you. It's not exciting anymore, so here's another application where we make also the embedded electronics and computing and sensing and so on into devices. And so this is another example of small robots. They don't look like fish. They look like maybe a small ball or a small ellipsoid. And these are made, for inspecting and perhaps repairing pipes and structures that are in confined environments, right? So that you can have a small robot that can go and do the inspection. So you can see this particular robot, when it moves, it doesn't leave any turbulence behind it, right? And then because of all of these sections here, right, the propellers are inside, right? And then you have the section, the length, the shape, right, and the location of these rim propellers, okay, so that when they are active, the flow becomes like very, very smooth and not turbulent in this way. And then you can make it, go into, these environments, and then do the mapping, recognize because a lot of situations when you have pipes, you believe it or not, in many places, whether they are water pipes or gas pipes or even in the petrochemical plants, that they add pipes and somehow forget to add them to the drawings, so that later on they either find maps, find pipes that were not supposed to be there, or because somebody did not record them. But anyway, so this is something that we have been working on. Another important topic is this intelligence, or the human-like intelligence. So maybe some of you doing vision. So if you look at this picture, you have maybe two teddy bears, right? These ones here, this one and this one. They look, in color about the same. Maybe the front one is a little bit smaller than the one in the back. But then for us, very easy for us to see, but for machine, if the lighting is different or so, it's not easy to distinguish between them, particularly when the colors are very similar. The other one is, in addition to understanding scenes, maybe another one, in making judgment and decisions. So here, this teddy bear, I know that it is flexible, so I can squish it into a smaller box, but then this is rigid, so it has to go into a larger box. And so how do we have machines that reason and then make these kind of decisions and also understanding? So one of the important projects that we have, with Professor Dmitry and his team here, is on the recycling of cell phones. This one is a very, very important project, not just for us as researchers, but I think for the environment and also for efficiency in cost. So you can see from this case is that if you do the recycling by selectively identifying components and removing them, from the cell phones, right, that you can have these kind of gains, like from 1 million cell phones, look how much you can gain in this one. The other way you can think of it is that if you take like a unit volume of phones, right, and then from which, if you use the maybe traditional way by shredding them and try to recover material from them, and doing it this way, the selective way, so with this method you can get maybe between 100 and 200 times, in terms of dollars or rubles, in that. So in order to have this, in order to have this, in this project, and we had the two teams, from Skoltech under the leadership of Professor Dimitri and us at MIT, identify a few things. One of them is how to, first of all, identify the components, right? Identify the components. This one is supposed to be running. So identify the components, their location in a precise way, and also the clearances, because when you open a cell phone, the components are small. The clearances between the components is very, very small. Just about maybe 300 microns. That's, maybe 3 hairs put together, right? How to automatically recognize these objects. Like in this case, you can see recognizing, let's say, a battery. This is doing it over the internet. This is why you see the video is not running smoothly, and also the pictures of the slides are not running smoothly. But anyway, so one way to do this, is the traditional way is to take maybe having a reference image, and then you take an actual image of what you see, and then you can compare. And this is kind of looking at the pixel values, and it's not really maybe that effective, particularly if the object is rotated a little bit, or there is a slight change in lighting, or even if there is some writing on the object, then it will have difficulty recognizing that. And so what we've done is to look into using maybe machine learning so that we can learn these very quickly, right? And then in the end, having the edges identified properly, as you can see in this output here, right? The edge of this battery is very clearly identified in that way. One of the ways you do this is by adding maybe some term in the loss function that emphasizes edges, and that is maybe one way of doing that. The other thing is, now that you identified the object that you want to handle, the next one is how to teach and how to learn the actions, right? So we would want to have maybe a human looking at a robot looking at a human doing something, and then the robot to learn from that, or looking at a robot looking at a video of you doing something, and then it learns from you, right? So, so in order to do that, you look at actions. So this is some videos that we looked at. These are by some other researchers, but we use their videos. They're on the internet to look at, try to identify, for example, somebody waving or walking or skipping, something like that. And these are like large motions. It turns out that when you do this, you find out that, for example, jumping jack up on the left and then jumping in place, the system recognize that very easily. There's no way for the algorithm to confuse the top action to this bottom left action, right? However, these ones confusing, right? You train and train and train, but in the end, doesn't get it 100% right. You can see in the numbers here, like for example, this one should be like 1, right? But it's not, because it's confusing it with something else. You and I look at this one, and we can distinguish between the two, okay? So this is an issue. Another thing that one of our students is also doing is that instead of looking at the whole video, maybe looking, because for us, when we look at videos, we don't look maybe at the whole thing. We just look at some parts of it, and then you get what's going on. So here is doing the same thing. Maybe at the top, looking at the whole video, but then taking like the segments from it here, there, and then processing them, right? And then you can extract the information in that way. So this is one of our students, Yin Nan, who has been working with us. And one of the tests was done on this public data set, Gesture. So there are about 50,000 videos, people doing all kinds of gestures, hand gestures, right? And then you try to recognize those. So in this case, the training was only about 2 days. 2 days is considered very fast. There are some times it takes weeks or months to train one of these systems, and then when you look at the accuracy, from the top 1 and top 5, you can get pretty good accuracy. And also in terms of speed, you do like about 80 frames per second, which is fast, and you can maybe even use it perhaps in real. Of course, in our projects, we're not interested in people jumping and clapping and skipping, but looking at the actions, right, and trying to recognize them. So in the process of disassembly of cell phones, we would figure that there are few operations that are important. One of them is pulling, unscrewing, peeling. This is for flexible cables that exist in these cell phones, or maybe priming, right? And so what you want to do is to have the robot maybe look at you, disassembling, and then it would learn from you, and then in the end, when you give it the new cell phone, that it will do the same thing and adapt as it's doing them. So we've done this in like a couple of ways. One using what you might call like pre-machine learning, algorithms. So this is using like the optical flow and trying to recognize that this is an unscrewing operation. This is like the optical flow and points of interest in it. And also here you have the optical flow and also points of interest in that video. And then you can identify, for example, that this is an unscrewing operation and that one is pulling. And then the other way to do is maybe to use like machine learning with different algorithms. Another thing that we have done in this area of learning is you can see here the robot will see you put the sequence together. You have, let's say, purple, blue, green, and red, like this, and you have on the side, on the top right, blocks that are colored, and you use them in that way, and then the robot will start filling, this one together like that, right? So the idea is that it will learn, and then maybe it teaches the other robots, right? And go from there. The other thing is, imagine that there is a robot and a human collaborating, but there are mistakes that happen, okay? So the robot in real time can see, what the mistakes are, and then it will correct them, as you can see in this video. So this is very important because the robot, by the way, is running several threads simultaneously. The collision avoidance, for example, the path planning, the execution, and then also the algorithm for identifying the scenes and doing this kind of task, learning and execution in that way. Sorry. How much time is it? 10 minutes, okay, yeah, so it's right. So of course you can maybe use similar things, maybe in the medical area if you're having maybe a robot teaching that. And then this is of course the work from Professor Dimitri with his students here in these manipulation tasks and maybe disassembly tasks and so on. You need to know also the forces and maybe the torques that are applied. And in his work, trying to look at maybe just the hand, and then from the color of the hand and the fingers as it's doing this task, that you can learn maybe these forces, and this is what this video is about. So you can see very small motion. The other work that they have done is in looking at, again, maybe at the fingers and using computer vision, the colors in the fingers, and then you can identify the forces that are, so this kind of work goes with the previous one that I mentioned, recognizing the actions and then the forces and maybe other details about those tasks that are involved in that way. Good. The other item is in the human-robot collaboration. I mentioned about Boeing before, there's nothing Boeing and maybe some other industrial companies where you need more machine and machine cooperating, machine and human cooperating in the same environment. And also on the right-hand side here, I mentioned earlier about Amazon. This is one of the solutions that seemed very simple. So this AGV will go and bring the whole shelf in which there is one item that the operator needs, right? But it turned out that a simple solution like this, increased, or made the fulfilling the orders by 4 times better, or at least 4 times. So I mentioned earlier about the Da Vinci robot. In fact, when I was doing this call it surgery on the pig, one of the other managers, got, because they had actually 2 consoles, one that you can see on the right and on the left. So he got onto this one, and then he can also have access to the tools, and so that he would be helping me. And he said, "Can I help you?" I said, "Sure." And then he took control over some of the tools and started doing things with me at the same time. We are two different places, right? And there is the pig on the table, and we're working together in that. So they have like collaboration and assistance in real time. This one is some work that we did before, right? And this is a system almost 20 years ago, right? Looking at maybe a system that does, think of it as it makes circuits out of optical fibers instead of our electrical wires. Like stripping, cleaning, splicing. Splicing is like connecting things. And then the machine has many different actuators on the top, maybe 5 micro manipulators, right? But then it does this. But the important thing is that this machine has maybe 20 actuators, maybe more than 80 sensors, vision system, a laser in it, right? But also you would want maybe machines like this, instead of giving it all the details, perhaps you can say, just connect, for example, fiber A to device B, and then it knows all the details that it needs to do, in between. And then the other thing is on type of speed, but I can skip this one. So this is the work, maybe you can say that it's not really robotics, but it is like imaging, at the nanoscale. This is another project that we've had for quite some time in the lab, developing instruments that can see at the nanoscale with very high precision, sub-nanometer precision, but at the same time taking videos of processes like this, right? So you can see at the top left, so that was calcite. It's material, you put acid in it, and then you're scanning, very mechanically, very, very fast, so that you can take the images in that way. So what we found out is that it's not like sugar. Imagine you had a cube of sugar that you put in your coffee or in your tea, and then it dissolves, all together. But this one, it happens that the solution, when you put the acid, you can see at the top left, that it happens in these layers that are retracting, right? And they retract along the crystallines of the material. You can even see the thickness of the layer, about 10 millimeter, 10 nanometer, right? And it starts at pits, you can see them here, pits that have about maybe around 10 nanometers in diameter, 1 nanometer in diameter, about 10 nanometers in depth, and then it transitions to the layer by layer, transitioning or dissolution. You can also calculate the rate at which this process is happening at different locations. So you can see a lot more than, in most cases, you have the combination at the beginning of the chemicals or the materials, and then the process happens, and then you see the end. And you have no idea what happened in between. So this is what we are trying to develop, these instruments, so that we can see the processes like in live. Like, for example, in this one where you have deposition of copper on gold, and maybe also stripping that material off of the other material, and you can see it live in front of you. So this one takes actually a lot of things. That is scanners that move, at the very, very high speed. You have optics. You have the interface, to move the data, from the machine to the computer. So in the system that we have today, we do about maybe like 20 million samples per second, right? And then, so all that data is transferred and then we process it in real time so that you can do the visualization and also taking data from it so that you can use actually information from the images for compensation and real-time control. Because this is very, very sensitive. It has like sub-nanometer precision, so anything that happens, vibration or so, will perturb it in that way. So there's another system that is being put together now, and so that one should have maybe around 60 million samples per second that you try to handle in real time. I'll skip this one. This area of monitoring and prognostics, I believe, is very, very important because when you have machines, you know, you don't want the machine to break, you know, all of a sudden, and then we have no idea what. So the health monitoring and definitely the prognostics in looking into the future, you know, the health of these systems is very, very, you know, important. It involves many things in modeling, the validation, learning, you know, prediction, you know, all of these themes. Maybe I'll skip this one because of time. And then like in the end, to do the monitoring is like looking at the performance at this time, right? Prediction or prognostics is predicting the health and the behavior like into the future. You can imagine maybe a system saying, you know, I am okay today, but maybe tomorrow at 2 p.m., you know, this part may not be okay, right? So you can know ahead of time. And then you have maybe systems that come in and then automatically, you know, remove the old systems in that way. So this one it says, supposed to be a new system saying that, you know, I'm here, you know, that to retire you so that you are out now and I'm going to take your place. I went a little bit fast and we covered a lot of these areas very, very briefly on them in terms of the instrumentation, embedding electronics and communication, intelligence and so on. And of course there are other ones that we haven't talked about, especially the power sources. You know, the batteries are very, very important, particularly for anything that is mobile. The brain-computer interfaces, so how you can have like your thoughts, maybe transferred automatically, you know, to a machine. And then the other areas that are important. And of course, there are other ones that are not on this slide. I hope that I convinced you that there are many, many themes and applications of robotics and automation that are very, very exciting. And there are a lot of opportunities, you know, not only for the research and development of ideas, but also perhaps for innovation and launching, you know, your own companies in these areas. So with this, I'd like to thank you for listening, and I'd be happy to try to answer any questions that you may have. Yeah, thank you.
Questions?
Is everything clear? And everything? Like looking to each other and say, oh, guys, in the world, people asking the question. Yeah, it's a good policy. If you have question, you must have question. Yeah? Because we're very interesting topic, and you can ask. Miguel, do you have question about the project? Scientists always have questions, yeah. Engineers, maybe not.
How could be thank you very much for your presentation. How could be the future for the integration of this like intelligence that we have in the human dexterity in the robotic systems? Because I think till now it's very, very difficult to arrive to one full automation of systems. So till what moment we can arrive, what point we can arrive in this moment with the technology that we have in our hands?
I did not understand the question before you did. Anybody understood the question? was a question, but I didn't understand most of it. Anyway, what I got is, as you know, a lot of this is already happening. Maybe some of them are already in products, particularly the ones that are really more software oriented. Other technologies that have been embedded already and implemented, you know, in cars and perhaps other situations. So as you know, some of them are not, are there, but still, not completely, performing at the level that you. I'm thinking of the Tesla, for example, the driverless cars. So yeah, you have the cameras can see, but then the system does not recognize, what is being seen. So I think in definitely the development of the technologies from the hardware, the sensing, the algorithms point of view is happening faster and faster. But then, in terms of their implementation, whether they are in the manufacturing, I mentioned this one application for the recycling, and just in that case, handling and manipulating and handling these very small and fragile components is in itself, a challenge. So, I believe that quite few of these technologies will reach, their maturity, and then they will be, used and performing, I think, at the level that you want. As I said, I could not understand the whole question, but only from some of the words that I heard that I'm commenting, and I'm here for today and tomorrow, so I'll be happy to speak with you more. Yeah, I think that was another question.
Professor, I want to ask, how do you think about the future relationship between human and artificial intelligence or robots? You think is it possible that the humans in the future will become a combination of real human and machine, like half part of human is human itself and half part is machine? It's a combination. How do you think about that?
So, thanks. Yeah, this is a good question. So, okay, so let me just say what I believe. I still believe that we as human, I think we are distinguished by our brain. And I still believe that there are things that we can do because we are distinguished by our brain that the machine cannot. Okay? Now, going to your question, the machine definitely can compute very fast, can analyze very fast, can maybe see some details that we cannot see. Yes, it can do that. The combination, of human and machines, maybe human and machine can work together in a complementary way. That happens. Now you have even, people who have been, researchers working on, these brain, computer, interfaces, so that maybe thoughts can be, and information can go back and forth, from the human to the machine, from the machine back, without any wires and things. So that is already, happening. You have already prostheses, for limbs, and the previous ones, were maybe not sophisticated, but the ones that are being made now, some of them are passive and more performing in a better way than the previous passive ones. There are other ones that are active. And so yes, all of this is happening, whether it's in the medical areas or so. And yes, and I think as these technologies, both hardware and software, being developed more and more, then you can see, I think, all of these things. And I definitely things that are maybe assisting, the human. So there's, for example, one of the projects in the media lab at MIT, so you can ask a person a question, but then that person is already connected to the internet, and then gets the answer very quickly and then responds, right? So whether it's a computation or it's a question about history or something else, so then the human is now linked to that knowledge that people have stored, let's say in the cloud, and then it uses them. So I think you can see, more and more of these things. Yeah. Thank you.
Wake up. And now.
So, first of all, thank you very much for your lecture. And I would like to ask a question. Now it's very popular, so to say, to bring artificial intelligence, neural network, machine learning into robotics fields. And in which fields are you feeling now and it will be more beneficial, and in which fields it's still more beneficial to use traditional control algorithms and methods? Thank you very much.
Thank you. So it seems that there were two questions in your question. So one about the control. So I see maybe the controls is maybe different from the learning, or they can be together in some way. And let me comment about the learning and the machine learning. So yes, so they have different algorithms and different methods that have been used. But I somehow think that this is, for me anyway, that it's like a brute force. Particularly the cases where you have to have a large amount of data, to learn. People, of course, use the analogy with like a baby, and a baby takes time to learn. But that is one thought. In my case, I'm interested in learning very fast. Learning with, let's say, a small amount of data. Because in a lot of the applications, and particularly the ones that we do with the companies that we work with, they don't have time. Whether it's in the manufacturing environment or it's in the real environment, it has to adapt, very quickly at that instant. The other thing is that there are some machines and some applications where the systems are so expensive, the company cannot afford to have it break down many times, so that this algorithm can learn from it, right? So in that case, one has to have a different way of doing it. So of course there are the people who are using the large data, the big data sets, for doing that. I would like to do things, with the small data sets, and perhaps like from videos, maybe I can learn just from one video, or one clip, or a few frames, right? Something like that. And then all of this learning, I think, combined, for the real-time, control, because that is, I see it as like they go together. One is like learning and helping you for decision-making and so on. And then the controls, depending on the application, if it's an industrial robot, for some applications, maybe just a PID, can be sufficient, right? And then there may be other applications that need maybe more advanced, control methods.
Just some comments. Last question. Comment that two of our students, and we are really very grateful that two of our students, Alina and Victor, who will come tomorrow back from MIT, they did wonderful research on convolutional neural network, applied for factory for dismantling, or in future, the Foxconn company has 1 million workers, 1 million, and your iPhones are assembled there. And what is doing now China in Foxconn company, they automating at highest level all industry for assembly. This is a big market, it's a huge market. And there, to train this robot and to extract information from the human, here the neural network is an excellent application. And we are doing this, yet to get this, Professor Kamal. Okay, last question.
Thanks again for the lecture. My question is actually a follow-up of the previous one. So I'm not a student, I'm not a scientist. I invest in technology, so I'm a venture investor in specifically in agriculture and food. So I wanted to ask your view on how robotics and artificial intelligence, like to what extent agriculture and food is applicable, today is applicable for those technologies in the range of all the industries. And if you had any experience in projects in this segment, this market.
I haven't done any work in the agriculture area, and maybe the food maybe in the manufacturing environment. We had that, stuff like that. However, I mean, you can imagine a lot of these systems, being used. For example, technologies in recognizing, let's say, if you have automated machines that are in the field, for picking, for example, apples or oranges or some other kinds of product. And now it has the intelligence that it is the same like a human, that it can tell which one is right when it's the right time for it to pick, for example. So that could be, I think, an important area. And then the other one, in terms of the food, what comes to my mind is maybe guaranteeing that the food, from the time it is produced and then transported and maybe stored, and then now for the human to consume, that there may be different things. For example, guaranteeing or having information from maybe instruments that could be even embedded in the packaging, for example, that can tell that the food is still fine, not just by the date, but that is perhaps one thing. Another one is maybe things that are related to the medication. There are people taking medication, but then the food also interacts with the medication, so that there can be like secondary effects just from that combination. So so there could be, I think, technologies that can help the user and the human, from these are maybe just a few that came to my mind. Yeah, unless you had something like specific that I can maybe answer.
Yeah, I was actually going to ask about one segment of
Please, yeah.
my chart, which was sorry, it was about one of the areas of opportunities, which is system monitoring and prognostics.
Yes.
So like when you have data from fields, for example, right, you can predict development.
Yeah. So that's also.
The environment is so complex, like, because it's not a plan with specific
Sure. Yeah.
operation. It's kind of
So most of the prognostics work, I would say, that has been done before is maybe predicting the state. So like maybe in this case, could be maybe taking the information, maybe building these learning systems, taking data from the past, maybe combining them with some other knowledge, and then predicting in the future, maybe if it is in the agriculture thing, maybe what the result is going to be, perhaps in the yield and so on, could be like in the short term, or perhaps if the models are really good, could be in the longer term, things of this sort. Yeah. Thank you.
Thank you. So as to agriculture, actually, just to make some comments, in DVI precision agriculture, this one of the opportunity for automation, and in Germany, there's many autonomous tractors. Yeah, they're already working. Australia and so on. The market exists, and the salary price and environment is too complicated for humans. So maybe the idea of robotics is to replace human in dangerous or kind of harsh environment. And that's the market is increasing because salary is increasing,
Yeah, and demand for automation is increasing, especially for Russia, because Russia is the biggest country in the world with very small population. And I always tell that this country should love robots. Yeah, a lot. Okay, thank you so much for your amazing lecture. Yeah, and thank